Hey guys, welcome back to the channel. In this video, I'll be introducing the idea of calculus. And throughout the video, we'll be talking about where the basics of calculus come from, answering the questions of what is calculus and the two basic ideas of calculus. So before we hop into the meat of the video, please subscribe to the channel, leave a like on the video, and comment down below. How's your guys' summer going? And any topics you guys want me to cover down below. Also, follow the channel on social media. Currently, right now, we only have Instagram, and it's YT_. With my tutor. It'll be in the description, and also in the first comment down below. So let's hop right into it. Okay, so what is calculus? So calculus is defined as the study of rates of change. So in Algebra 1, we said, okay, if we're given a linear function, all right, the rate of change of this is its slope. Its slope is the rate of change. So the rise over run. So this is the rate y changes in respect to x over time. All right, and that works, and that definition works for linear functions. Okay, but once we take it to a curve, we find out that that over a time period. So, like if we're trying to find the slope of this line in between a and b, how much it changes in between that, or how much the rate of change is in between this interval. Well, that's we call it the average, and that's f of b. And we found that was a similar formula: f of b minus f of a over b minus a. Okay. Also known as the difference, or another form, f of x plus h minus h minus f of x over h. All these are both known as the difference quotients, or also the slopes. But so then we also okay. So now imagine. So this brings us to the first idea of calculus, the instantaneous rate of change. Because not all the time are we going to want to find the average rate of change. So this works for the interval. But what if we want to know at this point how much did the function change? That's where the first idea of calculus comes from. It's what we call the derivative, and it finds the instantaneous rate of change. So imagine a car going from A to B. So traveling a distance starting at A and ending at B. All right. How fast it moves throughout A to B is its average rate of change. But if we wanted to find this C, that requires calculus. We could use the difference quotients, and using different rates of change getting closer and closer and closer and closer and closer, different values getting closer and closer and closer and closer to C, giving us pretty much giving us a close rate of change or a closer slope, but that's not. But it's just an approximation. Okay, and eventually we get so small that we end up using the limits, which we'll demonstrate down below with the most famous problem, the tangent line problem. This is what we call the tangent line problem. Okay, so for this, imagine having a curve. All right, and at point A, we're trying to find we have a tangent line, and the question is, what is the slope of the tangent line? Okay, well, we learned in algebra and also geometry that graphically, the slope of the tangent, so a slope requires 2 points, A and B. Assuming we don't know limits and assuming we don't know calculus, well, all right. So we take a point B, and that gives us a secant line, okay. And finding that slope, it gives us an approximation of the slope of A of the function at A, but it's not a really good one. So we take a point closer to A, and that gives us a better approximation, and that's labeled B prime. We take another point, even closer, and even closer, and it gives us a better approximation each time, over and over and over. Eventually, our approximations will get so small and so close together that we could use the definition of a limit, which we'll cover later on in calculus, or if you're happen to be lucky, in pre-calculus. But typically, most classes cover it in calculus, and pretty much the slopes get really close to where we say, okay, the limits as x approaches 0 is the difference quotient. So this rate of change of at point A is the limit as x approaches 0 of the difference quotients, and we say that equals the derivative. All right, and which we'll prove later on in calculus, which gets proved later on in calculus, which is a really interesting proof too. Okay, so the next point. So now that's useful, all right. And there's a second problem when it comes to calculus. All right, it's also known as the area problem, and this introduces the idea of the integral, which we'll prove in a later function, in a later video. And it's the most useful. It's one of the most famous problems that honestly, in my opinion, it's the most useful piece of calculus, especially for physics. If you're going to be using especially in work and momentum and impulse, this comes in handy. But both ideas come together to form everything we know about physics and calculus. So, but I just went on a tangent, pun intended. All right, so okay, so. Alright, so now going back on track. Say we're given a curve. Alright, so and we want to find the area of this curve at point A and B. Alright, in the interval of A to B. Alright, so this figure right here. Well, how are we going to do that? Well, geometrically, we could draw rectangles. Okay, we could draw some above the graph. Okay, sorry about that, guys. All right, and but we see that this is an under. So this won't give us the whole area because this gives us a little bit. There's a little bit under. So then, all right, so we could draw some underneath the curve. Okay, well, okay. I'm horrible at drawing, but all right. But as you guys see here, there's still this area right here that needs to be covered. All right, so eventually, so if we had more rectangles, the closer of approximations we get, despite there being some left, an overestimate and underestimate, the more rectangles we draw, the better the better approximation we get, and eventually it gets so small that we use the summation. We take the sum of all rectangles of the area of rectangles, and taking the limit of it gives us it gives us the area under the curve. And this is also and this is what we call the integral. This, you guys have probably seen this before. The funky S looking shape. Oops, bad example. The S right there, the shape. And so we'll cover that in calculus, but in calculus too. And so pretty much the first idea of calculus is the first semester calculus. Pretty much what we say is the differential calculus. This introduces derivatives. The second idea of, also known as the area problem, introduces the integral, and which is a whole basis for second semester calculus. And we take these two ideas together to form to form what we know with math. So going back to this car, all right, without the derivative, we wouldn't be able to do this. All right, we wouldn't have been able, without the first and second ideas of calculus, to make all the innovations we have in physics, calculus, or in physics and chemistry and biology, and all the scientific backgrounds we have. So, in conclusion, calculus is the most important tool for mathematics, and it is what actually led us down to the technological advancements, and also the scientific advancements down the years. I'll see you guys next video.